Okay, the idea now is to talk about the Hill cipher. The idea of the Hill cipher, let's start it, is again we are going to work in finite field z of m. Let's consider for the example m to be 26, and we want to take the plain text and convert it to ciphertext. And now the Hill cipher will use matrix multiplication or a linear transformation, if you want to call it, of the plain text in order to get the ciphertext. And this is the encryption part, and the decryption part will use the inverse matrix. So we need that the matrix we will use will be invertible. Inverse matrix to get from the encryption to the decryption. So you understand that there are some linear algebra games we need to do here, and we also need to be sure that the matrix we use is invertible, not just that it is invertible in the finite set that we use. In this case, for example, z of 26, for example. So this has some condition we need to satisfy in order to a matrix to be invertible, but not just invertible in the finite set. So the determinant should not be zero. This is for the general rule for a matrix to be invertible, but also it should also satisfy that the GCD of the determinant of the matrix and the size of the finite group should be 1. I write it down so it will be more convenient to understand. So I will say everything I said probably again as we do the Hill cipher. So let's start with taking a very nice and convenient to work with plain text that has no any logic in it. So let's take no. And this is my plain text, BADC. Why? Because it's convenient. Now I can translate it to numbers. B is 1, A is 0, D is 3, and C is 2. Yes, it's conversion to numbers between 0, which is A, to 25. So now I want to convert it to the ciphertext. How I do that? I use a key. The key is a matrix. Let's take 1, 2, and 0, 1. This is my matrix, and I need to see that it's invertible in the finite set. In order, I just remind you, for a matrix to be invertible, what do I need? I need that the determinant of the matrix will be non-zero. This is the general rule, but it's not enough in a finite set. But in a finite set, I need more than that. I need that the GCD, it's very like deciding if a number, if in a finite set has an inverse. What we need? We need that the GCD of that number and the size of the set will be 1. This is the condition for A to have an inverse, for which we will get this. For example, if I'll take the general rule. Okay? This is what happens in finite set. So for a matrix to be invertible in a finite set, what I need for a matrix in a finite set, what I need is that the GCD of the determinant of the matrix I work with, let's call it K, and the size of the set will be again 1. Now, note that this condition also tells me that the determinant must not be 0, but it's not enough. Why it must not be 0? Because let's assume that m not equal 1, okay? Because GCD of 0 and any number, let's call it n, is just n. And if n is greater than 1, then 1. So if I take a GCD of 0 and something that is not 0, the answer, the value, the result of this is just a non-zero value. And if I assume that the n is greater than 1, oh, yes, so this result will be greater than 1. So if the determinant here is 0, so the result will be m, and if m is greater than 1, the result won't be 1. Anyway, remember, the GCD of 0 in n will be just n. So it's quite, if m is not 0, it quite tells me also the determinant must not be 0. If m is not 1, so the determinant must not be 0. Anyway, this is the condition I need to satisfy in order for a matrix K in the group, in the finite set we are working in, to be invertible. The size of the finite set is n. Okay, this is the condition, and I assume that the matrix I chose satisfied. I don't even check it. Why? Because it's convenient. Also, I'll just give you the inverse of the matrix without proving it. I'm not sure I prove it. Okay, so we have the matrix. Now, note that I chose a matrix that is 2 on 2, the dimensions. What it means that I can convert every time 2 letters in the plain text. 2 letters. If I had a matrix of 3 on 3, I could convert 3 letters at a time. So, I have the plain text. This is the plain text. Let's take it here, right over here. I have the matrix right over here. Let's start encryption. And what I will do is this. Again, the matrix is 2 on 2, so I can every time encrypt 2 letters at a time. So I need to encrypt BA, which encryption means multiply by the matrix, and I will encrypt DC, which again tells me multiply it by the matrix. So let's do an example. So BA is like the vector 1, 0. This I need to multiply by the matrix K. So what will we have? We'll have matrix multiplication, 1 times 1 plus 0 times 0. Yes, this time this plus this time that. This is for the first part of the vector. For the second part, I will have 1 times this plus 0 times this. This. 1 times 2 plus 0 times 1. And if I had no mistakes, this will be 1 and 2. Okay? Great. Now I need to do it for the second part, which is 3.2. And I will do it maybe a little faster, which is 3 times 1 plus 2 times 0 and 3 times 2 plus 2 times 1, which will give us the vector 3 and 6 plus 2, which is 8, if I had no mistakes. So the ciphertext is 1, 2, 3, 8, and you can take it because I take this one and then this one. And now I can write it in letters, and 8 is A, B, C, D, E, F, G, H, I. This is the ciphertext. Now let's assume that you get this ciphertext and you want to decrypt the message. So, decryption. In order to get a decryption, I need to get the inverse of the matrix, because what I will do is take the ciphertext generally and multiply by a pair of 2 letters, as I did in decryption, by the inverse of the matrix, right? So let's calculate the inverse of the matrix. Okay, I won't calculate it, I'll just tell you what is should be the inverse of the matrix. Now, how you can calculate it? You can calculate it row operations, whatever you want. It's very green, if I can say, not very nice. You can use there is a formula that says 1 divided by the determinant of K of the matrix, multiplied by, I'm not sure if I'm right, D It's like the transpose D, A, B minus B, and here it's C and minus C and A. This is the formula for, and this is right like this. This is the formula for calculating the inverse of a matrix for a matrix of a size of 2 on 2. Now, I'm not going to actually go throughout calculating it. I'll just tell you that the inverse should be, if I remember correctly, if I'm wrong, I'm sorry, it's just the inverse of 1 minus 2, and this is here 0, 1, right? Yes, if I remember correctly, the inverse of this matrix just put minus here, and this is the inverse. But maybe I'm wrong. It doesn't really matter. The idea is that you will understand how to do the Hill cipher. So now I will take my ciphertext and convert it. I will decrypt it. I will convert it to the plain text again. So I'll take BC and uh, multiply by k minus 1, and I should get the result of the plain text. If not, so I had mistaken in the calculations. Sorry, it won't be so nice, but I wish you will get the idea. And k to the power of minus 1. Now let's calculate and see if it worked or not. So the calculation will be like this. B, which is 1, and C, which is 2, times this inverse. So k minus 1, which will be, let's calculate it, 1 times 1 plus 2 times 0, and 1 times minus 2 plus 2 times 1, right? This gives me, let's see, 1 and 0, which is good, which is BA. This is a good start because in the plain text we really had BA. Okay, that's good. Let's see how it continues. So DI. So I don't need to calculate it. And 3, 8. 3, 8 times the inverse of the matrix is, okay, let's look at the matrix. So it's 3 times 1 plus 8 times 0, and now 3 times minus 2 plus 8 times 1. 3 times minus 2 plus 8 times 1. Let's see. So we get a vector which is 3 and minus 6 plus 8, which is 2. This means that it is DC. So DC is the right one. Let's see. DC. Great. 3, 2. 3, 2. Yes. It worked. So this is really the inverse, or probably I was right. I mean, I took it from the inverse, but I'm not sure. I wasn't sure that it was calculated in the finite set that I worked with. So I just remember this for, and I remembered probably correctly. Anyway, the plain text or the decrypted, let's call it the decrypted ciphertext. Oh, yes. No, the crypted ciphertext, which is the plain text, is really the 1, 0. Oh, it's 1. No, so let's take it like 1, 0, 3, 2. Okay, which is B, A, D, C. And here it is. We decrypted the data using the inverse of the matrix. So this is the idea of the Hill cipher. Of course, I could take another matrix, another key, which is, I don't know, 3 on 3, and I will convert each time 3 letters, or I could take 4 on 4 matrix and convert 4 letters. And what will happen if I have text of 5 letters and I use a matrix of 2 on 2, namely each time 2 letters? I'm not sure. So, but this is the idea of Hill's cipher and how it works, and how the matrices are used, and how to know if there is inverse matrix in the finite set, and everything. Thank you very much. If there are any mistakes or corrections, please tell me. This was about the Hill cipher, and that's it.